Welcome back, dear students. So, in today's session, we are going to discuss about the various modes of heat transfer. Heat transfer happens as a result of temperature difference, right? But even though that temperature difference exists between two substances, depending on the substance, the heat transfer can happen in three ways, that is, conduction, convection, and radiation. Conduction happens due to physical contact, and if there is a solid and a moving fluid, it is termed as convection, and the highest rate of heat transfer happens in the form of radiation, that happens via electromagnetic waves, and there is no medium required. Unlike in conduction and convection, radiation does not require any medium. The three laws which govern the heat transfer are Fourier's law of heat conduction, Newton's law of cooling, and stephan-boltzmann law respectively. You can feel the various modes of heat transfer when you boil water on a gas stove. You can feel the warmth when you stand near to the flames, and the conduction when you touch the hot vessel. Directly heat will be transmitted to your body from the vessel, and convection when the water boils inside the vessel and the water particles are moving up due to the boiling process. You can see, you might have experienced, most of you might have experienced all these forms, but still you might not be aware whether the form of heat transfer is radiation, conduction, or convection. That's the only difference. So coming to the first mode, conduction, whenever there is physical contact between two bodies or between the hot part of a body to a cold part of the body, the transfer of heat is termed as conduction heat transfer. So there should be physical contact, that is conduction. So it happens at the molecular level. You can see that whenever there is heat transfer to a substance, its temperature increases and thereby it gains kinetic energy. Whenever heat lost from a substance, its temperature decreases as well as kinetic energy decreases at the molecular level. So at the molecular level, from higher energetic molecules to the less adjacent energetic ones, heat will be transferred, and that is termed as conduction. It can happen in liquids, solids, as well as gases. In liquids and gases, you know that the intermolecular distance is quite large when compared to solids. In solids, molecules are closely packed, and therefore the phenomenon of conduction varies in these substances. In liquids and gases, conduction is due to the collisions of the molecules, but in solids it is due to combination of lattice vibrations and energy transport by free electrons inside the nucleus. Now let us deduce an expression for rate of heat transfer by conduction and thereby state its governing law, Fourier's law of heat conduction. For that, let us consider a plane wall of thickness delta x, okay, of which the left side temperature is higher temperature T1 and right side temperature is T2 on either sides of the wall. T1 is greater than T2, and the heat is obviously transferring from high temperature to low temperature, that is from left to right, and uppercase A is the area perpendicular to heat flow, that is perpendicular to this plane. Fine, heat is transferring from left to right, so that plane perpendicular to the heat flow is the area. Okay. And Q dot represent the rate of heat transfer. Q is heat in joules. When it is expressed per unit time, it is joule per second or watts. Okay. So it is experimentally found that this rate of heat transfer by conduction is directly proportional to the area perpendicular to it, the temperature difference T1 minus T2, that is delta T, and inversely proportional to delta X, the thickness through which the heat is transferred. And the constant of proportionality is termed here as thermal conductivity denoted by K. Okay, we'll see that in detail later. Now, in this expression, when delta X tends to 0, in the limiting case, when delta X tends to 0, when the wall thickness shrinks to or it is negligible, in such case, that equation reduces to the differential form, that is Q dot conduction is equal to minus Ka dt by dx. Now, why minus sign? Why that negative sign? You know that in differential form, dt always refer to final minus initial, right? T2 minus T1. But from the previous slide, you know that T2 is less than T1. So obviously T2 minus T1 will be negative. But heat transfer in the positive x direction, okay, if you draw an axis from left to right, it is positive, right? Heat always transfers from high temperature to low temperature. So in the positive x direction, heat transfer is always positive. So in order to make this rate of heat transfer by conduction positive, this negative sign is added so that this negative sign and this negative dt is T2 minus T1. That is a negative quantity. So this negative quantity and this negative sign will get cancelled out so that you will get a positive heat transfer in the positive x direction. In watts. This is known as Fourier's law of heat conduction. This expression is the expression for Fourier's law of heat conduction. And this is a statement. The statement of Fourier's law of heat conduction. And now we have termed the constant of proportionality as thermal conductivity, which is a measure of the ability of a material to conduct heat. So how quickly, not quickly, how able the material is to conduct heat by penetrating through it. Okay. So how much the material is able to conduct heat, transfer heat through it. That is determined by the property known as thermal conductivity. It is a thermophysical property of the material. You can see from the table here, and it is expressed in watts per meter Kelvin. The unit for K is watts per meter Kelvin. You can deduce the unit from that expression. Diamond is having 2300 watts per meter Kelvin thermal conductivity, and human skin is 0.37 and air is having only 0.026. You can ascertain that air is a poor conductor of heat, right? So diamond is a very good conductor of heat as well as electricity. If you consider electrical conductivity, diamond is the topmost. Next is convection heat transfer. Now the second mode of heat transfer is the convection heat transfer, where there is a requirement of solid as well as a fluid in motion. The heat transfer between these two is termed as convection. You can see from the picture here, whenever there is some boiling of some liquid takes place, there will be continuous motion, right? Either by naturally or forced. So unless there is fluid motion involved, the heat transfer between the solid and a fluid will be by pure conduction. So you can see here, whenever air flows over a hot metallic block, so heat will be transferred from the hot block to the fluid in motion. So the particle which are in the neighborhood or sticking onto this solid, hot solid, the heat transfer between these two will be directly by conduction. Then one fluid layer will be sliding over the other layer. That's how the fluid motion is taking place, isn't it? So whenever there is such fluid motion takes place, the energetic particle that is in contact with the hot block will transfer heat thermal energy onto the next adjacent layer and next adjacent layer, like that. So automatically heat will be transferred from the hot block to the free stream fluid. So there are two types of convection: natural convection or free convection, and forced convection. So whenever there is no external source involved, naturally the hot air will rise up because of the density difference. That is natural convection. And whenever there is forced flow of a fluid over a hot body, hot object, that is termed as forced convection. So external blower or some fan are involved there. The heat transfer rate will be quite large compared to natural convection in the case of forced convection. The law which governs flow, rate of heat transfer in convection by convection is the Newton's law of cooling, which is expressed mathematically as Q dot convection, again heat transfer rate in watts, is equal to HA Ts minus Tf, where H is the convection heat transfer coefficient, A is the surface area. Instead of using the area perpendicular to heat transfer, here the fluid will be flowing over the surface, causing heat transfer between the solid and the moving fluid, right? So the surface area is involved in the case of convection heat transfer, whereas in the case of conduction, the area perpendicular to heat flow is involved, and Ts is surface temperature over which the fluid flows, and Tf is the bulk fluid temperature away from the surface. The free stream fluid will be moving without affecting the temperature gradient, right? So that temperature is Tf. So convection heat transfer coefficient H is not at all a property of the fluid, whereas K, thermal conductivity, was the property of the substance through which the heat is transferred. So heat transfer coefficient H is an experimentally determined parameter whose value depends on several variables like the surface geometry, whether the geometry is rough or smooth, the nature of fluid motion, whether it is natural convection, whether it is flowing freely or by forced. Then it depends on the property of the fluid like viscosity and all. Then also it is dependent on the bulk fluid velocity, at what velocity the fluid is flowing. The some values of heat transfer coefficient H, of which the unit is watt per meter square Kelvin. Watt per meter square Kelvin. The previous one was for K, it was watt per meter Kelvin. Here H, heat transfer coefficient H, lowercase h, it is expressed in watt per meter square Kelvin. You can see the free convection is having the lowest heat transfer coefficient, whereas convection, boiling and condensation, when boiling and condensation takes place, the heat transfer rate is the largest, 2500 to 1 lakh watt per meter square Kelvin. These are all experimentally determined. We can't predict it otherwise. Now the third mode of heat transfer is the radiation, in which there is no medium required and the energy will be transferring from one place to another in the form of photons or electromagnetic waves as a result of the changes in the electronic configurations of atoms or molecules. So in fact, energy transfer by radiation is the fastest. It is the fastest, and the rate of heat transfer is directly proportional to the fourth power of temperature. The fourth power of temperature, the rate of heat transfer in radiation is proportional to. So it is a volumetric phenomenon, right? The convection, you know that is a surface phenomenon. The conduction also, it is across the object, right? It is penetrating the object. But here, radiation, it is a volumetric phenomenon, and all solids, liquids, and gases emit. It will be emitting or absorbing or transmitting radiation of varying degrees. Even our human body emits radiation or absorbs radiation. So you can see here a person, even though that person is sitting away from the fire, he can feel the warmth of the fire, right? Through radiation heat transfer, even though it does not touch there, or even there is no movement of air between, still the person can feel the warmth. So the governing law of radiation is stephan-boltzmann law, where the maximum rate of radiation, which is stated as the maximum rate of radiation that can be emitted from a surface at an absolute temperature Ts. Okay, all these temperature values, whenever you substitute in Fourier's law of heat conduction or Newton's law of cooling or in stephan-boltzmann law, should be substituted in Kelvin. Okay, don't forget that. It is given by the stephan-boltzmann law, and Q dot emit max, maximum amount of radiation that can be emitted from a surface is given by sigma A Ts to the power 4. A, you know that the surface area, Ts is the surface temperature, and sigma is the Stephan-Boltzmann constant, whose value is 5.67 into 10 to the power minus 8. It is very easy to remember. 5678. 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. So it is a Stephan-Boltzmann constant. The idealized surface that emits radiation at this rate, that is the maximum amount of radiation, is termed as a black body. A black body can emit radiation at this rate. So radiation emitted by all real surfaces other than black bodies are less than this value, which are expressed like this by adding another, multiplying this expression with another parameter known as emissivity, epsilon. Emissivity epsilon is added along with the sigma A Ts to the power 4. That is the emissivity of the surface. That is the rate at which the ability of a surface to emit energy. The black body is having emissivity of 1, all other bodies will be having emissivity less than 1. It is between 0 and 1. So you can see the emissivity values of different materials here. A black paint is having 0.98, white is having 0.9, a polished silver is having the least 0.02 in this table. Now another property with respect to radiation is absorptivity. It is a fraction of the radiation energy incident on a surface. Suppose some energy is falling on a surface. We can't say that the entire energy falls on that surface could be absorbed, right? That will depend on the surface. So the fraction of energy that is absorbed by the surface is termed as, the ability of that surface is termed as absorptivity. Absorptivity. Like emissivity, its value also falls between 0 and 1. So black body again is the highest here, which is having absorptivity equal to 1. So black body is a perfect absorber as well as perfect emitter. So now another law states that emissivity equal to absorptivity. That is, emissivity and the absorptivity of a surface are equal at the same temperature and wavelength. At the same temperature and wavelength, both these properties, emissivity as well as absorptivity, would be equal. So the difference between the rates of radiation emitted by the surface and the radiation absorbed is the net radiation heat transfer. That is what we are going to see, the expression, the net radiation heat transfer between two surfaces or between a surface and the surroundings. It is determined from this expression. So instead of sigma epsilon A Ts to the power 4, we have added another term here. So between these two surfaces. So till now we have expressed only how much energy is emitted. This is the radiation heat transfer between two surfaces. Suppose radiation is coming from a heat source to the atmosphere. We can use this. Or if you want to calculate the radiation intensity which is coming from the sun, you can calculate this. So with that, we will wind up the session on modes of heat transfer. If you have any questions, please use the comment section below. You're always welcome to give suggestions and feedbacks. Thank you for watching. Have a good day.